Welcome back, everyone. In this video, I'll be going over the optimization lecture. So we'll go ahead and start with what is optimization? What does it mean? And this is really the culmination of applications of derivatives. We saw one main application of derivatives in a previous section dealing with related rates and exponential growth and decay. And those were just talking about sort of rates of change at certain points. We didn't necessarily care to optimize. Well, optimization is a really important concept because it deals with finding the maximum or minimum of something given some conditions. And some common examples are, the first one's probably the easiest to explain because it deals with money. It's maximizing the profit of selling X amount of product. Now, in general, figuring out the profit function of selling a product and selling X of them is very, very challenging. And since this isn't really a business type class, we're not going to go over these examples, but in general, when you optimize, you figure out an equation and then you just do what we did in the previous parts of this class. We find the absolute maximum, absolute minimum, whatever we want to do with that function. Some other things that might make a little more sense, are a little more relevant to this class, is finding the minimum amount of material to make something of a certain size. So you could imagine this is very useful. Maybe you want to fence in a certain area. Maybe you live out in the country, you don't really have anyone around you, and you have a big property and you want to fence in, let's say, 1,000 square feet. But you have maybe some terrain that's hard to deal with. You can't build a fence certain places. So you want to figure out, how can I build the smallest amount of fence, or use the smallest amount of fence by the minimum amount of wood to actually fence that amount in. And on the other coin, you can do sort of the same thing. We can figure out or find the maximum amount of area given the amount of material. So you can sort of flip that and say, I already went to the store, I bought 1,000 feet of fencing, and I want to know what is the maximum amount of area I can put in this fence if I want, let's say, a rectangular shape. And then another one that's pretty common and important is minimizing distance. So why this one might be important, pretty morbid but important example would be something like an asteroid is traveling close to Earth. When an asteroid gets really close to Earth, it actually passes by in almost a straight line. And so what people do to figure out, how close it's going to come, you always hear these reports, is they figure out the minimum distance based on where Earth is and pretty much the equation of the line. And we'll actually see a problem like that as well. But you can do a number of things. It can be really any quantity you want, and then you want to maximize or minimize it. You just need to be able to figure out the equation. Right. So this can be the big difference between related rates and optimization. Is related rates we just kind of did. We didn't have to know about maximum or minimums and how to find them yet, but that's all optimization is about. So I have some general guidelines to finding the maximum or minimum. Now, in general, what you want to do when you find or optimize something is you don't want just any maximum or minimum, you will want the absolute. So you could imagine if, maybe this above example with the asteroid, we figured out all the critical values, make the sign chart of the first derivative or something like that, and we see we have two minimums. Well, if one minimum is 1,000,000 miles and the other one is 100 miles, we don't want to, assume that it's going to come at minimum 1,000,000 miles, because 100 is significantly closer and a lot more terrifying in this situation. So we would want to make sure we're finding the actual minimum. Right, so that's something to be on the lookout for. Now, in general, what you're going to do, it's very helpful, is to draw a picture. Some problems you will be given an equation already, so you don't necessarily need to do this. But if you're not given the equation to maximize or minimize, you draw the picture. Then you create your equation based on your picture. Think about areas, volumes, equations. When we talk about the distance, you have the distance equation, and you may not have used that in a while, so you'll be reminded of that. But all sorts of stuff like that. And then what will often happen when you create your equation is you'll have two quantities. So imagine you are doing distance. The distance formula has an x and a y in it. And what you're going to have to do is use something about your problem to make just x or just y. Because to maximize or minimize something, we have to do the derivative. And we only know how to do that with one variable. This is not going to be something like implicit differentiation where you can do the derivative of both sides. It's going to be just regular differentiation. We need one variable. And this pretty much happens in every problem where you make your own equation. So we'll get practice with this. Then we do the derivative and find the critical values. If your problem has endpoints, only include the critical values inside. So something like that, if your problem is representing time, you naturally have a endpoint at t equals 0. So any critical value with a negative t value is not important or relevant. And you could have maximum values as well. Let's say you were selling a product, then maybe your X value, the amount of product, you can't reasonably sell more than 1 million of whatever you're trying to sell. So that would be its, a maximum upper bound or an endpoint. And then what we'll use is we'll use methods in previous sections to find appropriate absolute extrema. Now, one thing we did way back in the first section on maximum minimums is absolute extrema if we had closed intervals. So we had 2 endpoints. If you don't have 2 endpoints, then you're just going to have to make a sign chart and see what is appropriate. Where is your absolute maximum? Where is your absolute minimum? So we'll keep track of that as well. One nice thing about word problems and optimization problems is that if you set up your question and equation correctly, if you need to find an absolute minimum, let's say you're trying to minimize something, you should get an actual absolute minimum. You shouldn't get something that can shoot down to negative infinity or something like that. You set it up correctly and then everything will work out. All right, so we'll go ahead and start with the first problem. And yeah, I kind of picked this one to be a little more careful as far as shapes go. So most of the times you're dealing with shapes, you're probably going to deal with just a rectangle or just a circle or a box or something like that. But a Norman window has the shape of a rectangle surmounted by a semicircle. And what that is just saying there's a rectangle and on top of it is a semicircle. And all this little dashed line here that I have separating is just for visual reference. It's just pretty much looks like a rectangle with a rounded top. Okay. Now it says if the perimeter of the window is 8 feet. So if we go all the way around the window and we get 8 feet, we want to find the value x so that the greatest possible amount of light comes in. All right, so let's go ahead and read that. It says, if the perimeter of the window is 8 feet, this is sort of our condition. This is what we have to use to solve our problem. You're always going to be given some condition. And the perimeter, if you think about the perimeter in this problem, well, it's not just the rectangle. I know that's a word we use for the rectangle. It's going around the entire outside. So it's these 3 sides of the rectangle, but then around the semicircle as well. So if we add all these links together, we would get 8. Now, one thing you want to go ahead and do is you can actually make sure you can write this equation down. So we don't want to just say added together equals 8. We want to write down actual equation. Well, the one thing that's going to happen here is that this side of the rectangle, so I shouldn't have done the bottom because we know the bottom's x. But this side of the rectangle, the left and the right, we don't have any possible understanding of what this number is. So we have to give it a new letter, and I'm just going to give it y. So if we start by adding together, we got y plus x plus y. And now the tricky part might be, how do you find the perimeter of this semicircle? Well, the thing is it's a half circle. And the word we use for circle as far as perimeter goes is usually circumference, how far you walk around. And the circumference perimeter or circumference formula is 2 pi r, but since we're only going half around, it's 1/2 times 2 pi r, which is pi times r. So if we go around this, it's pi times the radius. And we know the radius is half of the diameter. The diameter is this all the way across. So the radius is half of that. So it would be plus pi r. But we want to make sure we have as few variables as possible. And in general, you can have 2. If you have 3, then you need to do something to get it down to 2. And the main thing about this problem is that your x, which is the length down here, is also the diameter. So this x is the length of the bottom side here, but it's also the length of the diameter. So this is also x. And that means 2r equals x because x is the diameter. So r and another r add up to x. Now what you want to do is plug in and get x, because at the end of the day, we want to solve for x. So you don't want to get rid of x in your equation. You want to get rid of r. We go ahead and divide by 2. We get r equals x over 2. And we can plug that in right there to our perimeter equation. And we have y plus x plus y. Well, I'm going to make that 2y plus x plus pi times r is now x over 2. And it's up to you how you simplify this. What we can go ahead and do is, since we have an x here and here, we can sort of think about factoring the x out. And we have 1x plus pi over 2. Oops, this is supposed to be a plus, not an equal. Go ahead and fix that real quickly. So this is our perimeter equation. The 2y is this side and this side. The 1x is the bottom side, and the pi over 2x is the semicircle side. And this is all added together to equal 8. So we do have our condition equation. This is our condition equation. This is not the equation we're trying to optimize. Now, if you have just a rectangle, just a box, just a circle, this is much quicker to make your condition equation because you would have just the 4 sides of the rectangle. You don't have a pi without a pi. But I wanted to show you this one because I think this one, if you can do this one, you can do the easier versions. So we have our condition equation. And now what is the equation we want to optimize? Well, if you read the question here, we want to find the value of x so that the greatest possible amount of light comes through. Well, this is a window. So you have light coming through the entire thing. All right, so even though it's like a semicircle on top of a rectangle, it's still just a window, so it comes through the whole thing. And that means the area is what we want to optimize. The bigger the area, the more light that comes in. And specifically, we want to maximize it. So we don't want to minimize the area because what's that going to do? That's going to give us the minimum amount of light. We want to maximize the area. Now, what's the area of this shape? Well, the area of the rectangle is x times y. I'm actually going to go ahead and write area of rectangle plus the area of the semicircle, because we can just add the 2 areas together. And the area of the rectangle is the length times width. Well, we called one side length x and one side length y, so it's x times y, plus the area of the semicircle. Well, the area of a circle is pi r squared, so it's 1/2. It's half of it, pi r squared, but we know r is x over 2. So I'll just kind of write that on the side because we already figured out what r is. We know the area of a circle is pi r squared. Since it's half of it, you do 1/2. And we already figured out that r, we don't want to use the letter r, we want x with x over 2 in place of r. All right, so here comes maybe the tricky part. This is going to be really the annoying part of this problem is we want to do the derivative of this because this is our area equation and we want to maximize it. We only know how to do the derivative with one variable, so we cannot do the derivative of something with x and y. Well, now we use the condition equation and do the following. We solve for y. So we'll take this equation and solve it for y, which is right there, and then we'll plug it in right there. And once again, one thing I'll emphasize is that this problem intentionally is a little bit messier than if you, or actually not a little bit, it's a lot messier than if you have just a rectangle or just a semicircle. All right, so let's go ahead and solve this condition equation for y. Well, you can subtract this whole thing, 1 plus pi over 2 times x over. So we got 2y equals 8 minus 1 plus pi over 2 times x. And then you can divide everything by 2. So I actually like to do it like this. You can divide the whole side by 2 if you want, but just because 8 over 2 is going to be 4, I'm going to divide it like that. And we get y equals 4 minus 1 plus pi over 2 all over 2 times x. And now because we are going to plug this in and try to do the derivative of it, it might be helpful to do one more step. And that is just take this 2 and shove it in the denominator of each of these because it's in the bottom. All right, so the 1 over 2 becomes 1/2. So we got 4 minus parentheses 1 over 2 is 1/2 plus pi over 2. And then when you throw this extra 2 inside the denominator, it becomes pi over 2 times 2, which is 4. Okay. So this is what y equals. And yeah, it's not great, but it's what we have to use. So that's what we plug in right here. So we have the area equals x times, and then in parentheses, 4 minus 1/2 plus pi over 4 times x. And then plus, and then this thing we can square out the x over 2, so we get x squared over 4. Since we have a 4 here and a 2 here, become 1 over 8 times pi x squared. Now keep in mind what you want to do here is you want to do the derivative, set it equal to 0, and solve it. Get the critical numbers, and then hopefully if you have more than one critical number, you can figure out which one corresponds to the maximum area. Right. Well, as this stands, you can do the derivative because there's just x, but if you distribute this x through, distribute it to each part of the parentheses, then at least you won't have to use the product rule. You can just use regular power rules and everything like that. So when we distribute that through, we get 4x minus, and then we have 1/2 plus pi over 4, and then x times x is x squared, plus 1 over 8 x pi times x squared. That's just the end. And then if you want, you can go ahead even further now, and this is up to you, and distribute the minus through because you have an x squared here and an x squared here, or you can really just leave it alone. I think for the purposes of this, because we have this minus, if we distribute it, we're just going to get 3 terms with x squared. You could do something to kind of bring this inside and make this something times x squared, but you have to be careful with the minus here. So I'm going to simplify this. If you're not comfortable with this step, just don't do this step and do the derivative from here, because you can do it from here. We got 4x minus, and then I have my 1/2, my pi over 4. Now what happens if I bring this inside is I get a minus, and it's 1 over 8 pi, which is pi over 8. And then I have the x squared on the outside. Let me go ahead and kind of draw an arrow as far as what we did. I brought this 1 over 8 pi, which is the same thing as pi over 8. I brought it inside here. Because of the minus, I have to make up for it by adding a minus here. So imagine distributing the minus back through. We get pi over 8 x squared, which is what's on the outside. Okay. Now, as far as the area formula goes, it's not going to get any better than this. All right, but now we want to maximize the area, so we want to do area prime. We want to do the derivative, and you can write it as that prime, or because our letter is x here, you can do dA over dx, whichever one you prefer. I'll just write it as this because I already wrote it, d area over dx. We do the derivative of this. The derivative of 4x is just 4. minus the derivative of this. We bring we leave the number in front. We have 1/2. Now pi over 4 minus pi over 8 is actually positive pi over 8. So let's go ahead and just simplify that because we can. And then when we do the derivative of x squared, that is just 2x. So kind of simplified this to pi over 8. So inside we really have 1/2 plus pi over 8. And then the derivative of 4x was 4. The derivative of x squared was 2x. Well, now what do we do when we find the critical numbers is we set it equal to 0 and we solve it. So let's go ahead and solve this. You have 4 minus this equals 0. Go ahead and rewrite it. 4 minus 1/2 plus pi over 8 times 2x equals 0. Now you can subtract the 4 or add this whole thing over. It doesn't matter. I'll just add this whole thing over so I don't have the minus sign. I got 4 equals. I'm adding this entire thing over. So I've got 1/2 plus pi over 8 times 2x. So I added this whole thing over. And now what do we do? Well, now you're going to divide everything by what x is multiplying. And it's very messy. Our answer here is not going to be nice because of the shape, but it's the best we can do. We've got the divide by 1/2 plus pi over 8 times 2. And just the reason I have not distributed that 2 through is I knew that the 2 would cancel out with the 4 over here to make it a little bit simpler. So we got x equals 4 over 2, which is 2. So the 4 cancels out with the 2 here. So we have just the 2 on the top, and we have 1/2 plus pi over 8 on the bottom. Now, typically we don't like fractions inside fractions, so I wouldn't stop here, but you only have one step to go. If you stopped here, it wouldn't be wrong. But if you go ahead and multiply through by 8, that'll get rid of both fractions here because 8 will cancel out with the 2 and also the 8. And we just have to multiply by the same thing on the top to keep everything balanced. And we've got x equals 2 times 8 is 16 over, and then 8 times 1/2 is 4 plus pi over 8 times 8 is pi. Now we'll check that this is actually a maximum, but one thing that usually works out with word problems is that if you set up everything right and you only get one critical value, so that's a big thing. If you only get one critical value, then it's, as long as you set up everything, it is going to be a maximum. All right, now how can you figure out if this is a maximum or a minimum at this x value? Well, there's kind of two ways to do it. We can make a number line, or we can do the second derivative test. And we saw before that the second derivative test, it can fail. But what it says is that if you do the second derivative, now keep in mind we have the derivative formula here, so we just do the derivative of this thing. If we do the second derivative and plug in this number, as long as it's not 0, it'll tell us something. So let's do the second derivative. I'm going to do the derivative of our derivative, which is right here. We have d squared area, or just a, over dx squared. And what's the derivative of this? Well, the derivative of 4 is 0. Then we have a minus. We have this number, 1/2 plus pi over 8. And then we have 2x. Well, the derivative of 2x is just 2. So this is the second derivative. And notice that there's not even an x there. So it cannot depend on x. We don't even have to worry about plugging it in. We can just see, is this positive or negative? Well, all these numbers are positive, and then we're multiplying by a negative sign, so it's actually negative. And what you want to remember is that when the second derivative is negative, we have an absolute, well, it's actually a local max, but because it's the only critical number, it's the absolute max. Okay, so it's got to look something like this. It can't turn back around because it's only got one critical number, which means there's not going to be a local minimum. That would mean that we have two critical numbers. It's only one critical number. Right, so we do in fact get an absolute maximum for this x value. Once again, I just want to repeat what I said at the beginning. This is probably the hardest question of the section that I can think of just because of the shape. Now, we also had to come up with the area formula, and basically when pies mix with not pies, it makes everything messy. If you have just circles, just spheres, just a cylinder, things like that, it'll be much more straightforward. But I'll see you in the next video.